generally, if we have f as a function of x, y, and x is a function of t, and y is a function of t, then we can analyze the behavior of the graph at a point which is x of t, y of t, f of x of t, y of t. That is, we evaluate the function at values of x and y that are dictated by the value of t, and the coordinates at this point are dictated by the value of t. If t changes by some amount, then the x-coordinate will change by x prime delta t, whatever the derivative of your x function is. Your y-coordinate will change by y prime delta t, and you'll end up at a point out here, and I'm not going to label that. It'll be x of t plus delta t, y of t plus delta t, f of x of t plus delta t, y of t plus delta t. Okay? And you could write that down. Just keep your wits about you and think about what's going on. Now, for this function f of x, so the derivatives of x of t and y of t, that is the x of t functions along with the delta t, give you the derivative times delta t, which is the change in the value of x, the change in the value of y. Now, due to the nature of the f of xy function, you have some slope. Okay? The slope is partial of f with respect to x evaluated at this point. So that's the slope here. And along here we have a slope maybe I can write it here. Slope partial f with respect to y, evaluated again at whatever point you get here. So that in this direction, the rise equals slope times run, maybe a little hard to read, which equals what? Well, I'm going to write the slope first, partial of f with respect to x, understanding that that's evaluated at the coordinates of this point, multiplied by, instead of x prime, I write dx dt times delta t. And then over here, the rise, it's going to be hard to find room to write this, I'll try, rise equals slope times run, I'm not going to write that out, but that's going to be partial of f with respect to y multiplied by dy dt multiplied by delta t. So that the change in z, and of course let's be sure we understand that from here to here I'm going to rise by this much. So I could draw a rectangle here that's a little bit higher than the original rectangles. Okay? And then on top of this, I'm going to have to draw a segment that's very much similar to this one. The reason for the great similarity is simply that this distance is presumably small because delta t is presumably small, so that the derivatives won't have had time to change much between here and here. So the smaller delta t is, the closer this slope is to this one. But we assume it's quite close. So now we have the rise due to x and the rise due to y, and they stack on top of each other, so we get the total rise. And I probably ought to make that a one-directional arrow. Okay? So, this rise plus this rise gives us the total rise. So we say that the change in z is equal to this rise here plus this rise here. If we divide through by delta t, we get the delta f over delta t equals partial f with respect to x times derivative of x with respect to t. Looks like a chain rule, doesn't it? And partial of f with respect to y times the derivative of y with respect to t. We have to add the change due to the motion in the x direction to the change to the motion in the y direction, due to the change in the y coordinate. Okay, in the limit, this is just the derivative of f with respect to t. Okay, because as delta t goes to 0, all the approximations become exact. Small delta t, everything shrinks down, approximations become accurate. That's the meaning of the differential.